Alright, this video is for those who want to make some improvement, though it's not a complete retest, on their second storm exam, and I will go through it question to question and let you retest. So I'm going to go with review here, starting. First off, you just got done with a project. You should all know that in central Wisconsin, 100 year, which has a 1% chance of recurrence according to the Gumbel distribution of history, which is no longer correct, is 6 inches. 25 year is 4.8, and a 10 year is about 4.2 inches per day, right? That's inches in a day in a 24-hour storm. All right, so that's what is the rainfall depth. Again, these vary and they kind of can change with history, but we'll kind of continue down here, see if we can go down in through this thing. I don't know if I can grab it. Get the question. There I go, down. Okay, those are the three there. Curve number for paved areas. By now you should know, you just got done with the project. 98 for paved and 58 for a type 2 meadow. Those are the only two that you are required to know and use. However, usually it's a weighted average between those two. Range of velocities. Range of velocities we've talked about on and on in terms of between 10 feet per second down to 3.33 to make things relatively easy. So we'll see what happened here. Summary of data stored in this. I'm going to sign in. Somehow I lost my file. So we do that so we don't have to memorize a whole lot of other capacities. Because if you know the area by some rule, I don't care what rule you have, but if you know to put things in square feet, you have a range of 3 to 10, you should be relatively okay. So let me zoom around here and try to find that document now. So don't want to do there. I want to go to even more. Go back to my documents. So the reason why you grab things like we're grabbing them is so you have a minimum amount. It may seem like a lot, but that's a minimum amount of knowledge to know 3 to 10 when it's going to that, and a rule of how to calculate areas in square feet gets you capacities. Standard units of flow in the Imperial system. Incredibly important. A large part of what we've talked about all semester is cubic feet per second. We'll go back at the end of this to the kind of the graphic that we have that doesn't have flow on it, but it has cubic feet on it. So the standard of flow would be volume over time, so it would be cubic feet per time. Standard units of flow in the SI, System International Units. That is not Greek. It is French, System International. SI units are not imperial, they are metric. That is not meant to throw anyone. That interchangeability of SI and metric should be now core knowledge. Narrative form of Bernoulli's equation. And as I did it incorrectly first, basically what it was, the energy per pound due to position, per pound of material or water, plus the energy due to pressure per pound of material, plus the energy due to velocity per pound of material, plus the energy due to the pump, equals, along a flow path line, the same, plus the energy lost per pound of material. Now, if you want to learn this, once you understand what head is, you can say that it is the position head, plus the pressure head, plus the velocity head, plus the head of the pump. And eventually you can say it is the piezometric head, the piezometric head being Z plus P over gamma, because there's a lot of trade-off that goes between those two. But we recanted that, and understanding that as a core formula is considered one of the competencies of the course. So that's why the narrative, when you're given the equation, should not be so tough, and you want to start to look at a lot of equations that way, as not just equations, as summaries of knowledge in which you can apply other things. So I'm going to keep going here, hopefully. That narrative equation, right? Narrative is written out. If you're not familiar with that word, you had to do a narrative for your storm. All right. I'm going to keep going here, if I can. What does Q gamma work out to be? I'm going to go here, home, new slide. Q gamma works out to be pounds per second. Q gamma works out to be pounds per second because Q is defined as cubic feet per second, and gamma is pounds per cubic foot, and when you cancel those, multiply them together, you get pounds per second. Remember, I talked about Q gamma being one thing you'll see a lot of, and the other one being G sub S gamma, which still has the same units of pounds per cubic foot because specific gravity is unitless. All right, the hydrograph is a graph. Believe it or not, we've looked at a number. You did them in your projects. They have units. Along one side is cubic foot per second, and this is time, which you can always multiply out to be seconds, and so you get the area underneath being cubic feet. You'll see that knowledge of being able to calculate area under was something you were exposed to, at least in physics, when you looked at the area under the acceleration curve being velocity and the area under the velocity curve being position. And then went back with the slope of the position curve being, with respect to time, being the velocity, and the slope of the velocity curve being the acceleration. You will see that again no matter who guides you through it. Now you're on to the normal range of velocities of pipes. And so you have to do that as a two-step problem. You have to know the area and then the velocity. A 21-inch pipe compares to 24. It's smaller. 21 divided by 24. Then you square it, multiply by pi, and then multiply by 10 for the top end for 3, and divide by 3 for the bottom end. So area, that's why you learned to calculate areas. You had a calculator on this exam, so you could have taken 1/2 of 21 inches to convert it to feet, but once you grasp the compare and square, the pi is always there, it becomes much, much more efficient. Number 13, I will do it here, but it is a straight volume calculation of a cylinder. So basically what you're looking at, I'm going to go home, new slide. Converting to base units, convert to base units, and so you have given 120-inch internal diameter, that is 10 feet, right? That's its diameter. 10 compares to 5 to 2 because it's the unit circle is a 2-foot diameter pipe, right? 2 foot, and the area is pi. So this is going to be 25 on the top, pi square feet, times a length of 50 feet, and in that you have your answer of 50 times 25, so that's 1250 pi cubic feet. However you want to do that, it is a straight cylinder calculation. That is, there's nothing complex at all about that if you put things in standard units. The next one also comes, at least historically, from estimating. You have elevations of, at 100, you have 4,000 square foot. At 102, you have 5,000 square foot. And at 104, you have 8,000 square foot. And so average end area method, you can use a program or estimate, but the fact is you need to be able to look at these two. Say the area is 4,500, multiply by 2 and get 9,000 cubic foot between those. And you need to look at this at 5,000 plus 8,000, divide by 2 times 2 gets you 13,000, right? Since we're going in 2 feet, it works out pretty well that you get 22,000 cubic foot. That's in fact what you did with HydroCAD as well, or in estimating, or in any other of things where you know that the one formula for volume is area times thickness or height, and the areas are often averaged, called the average end area method. Theoretical freefall velocity of that number, we did it in class. It's the square root of 2gh. Some people left the h outside. We also did it enough times that you have to realize now that if we take the square root of 2 times 32.2 times, in fact, 155.28, we get that 100 foot per second. Bernoulli's equation, physics, whatever you care to, it is the work energy theorem. For that distance of 155.28 feet, there was a force applied. That was the weight. It caused an increase in kinetic energy. The 550 comes from 550 foot-pounds per second equals 1 horsepower. You continue through here. These next ones are pure conversion problems. I won't work them out, but I will work them on the board, as we say. You could do that any number of ways, but effectively, I'm going to go home, new slide. Here, we want to go with 7 cubic foot per second to, if you think about it, gallons per day. And it is a straight conversion. If you think about it, you can go from, put the cubic foot here, the gallons on top. You know that 7.48, and you were given a sheet equals 1 cubic foot. You now have the seconds and the days, however you want to do that, but it's 86,400. So that gets you the calculation for gallons per day, but million gallons per day, you just divide by 1,000,000. Pump flowing at 300 gallons per minute. What's the flow rate in CFS? Once again, a straight conversion calculation, whatever the case would be, 300 gallons per minute to cubic feet per second. This, of course, being the standard we are always shooting for, even though we're given this whenever we're dealing with pumps. So gallons per minute, you're going to multiply by, put the gallons on the bottom, put the cubic feet on the top. 1 cubic foot, 7.48. And you want to go from minutes to seconds. You put the minutes there, you put the seconds there, you make that 1 minute and 60 seconds, and you multiply out. At some point, one might program one's calculator to do these things. That would be better than having a program provided to you if you're doing enough of these, but you do then not want to be able to do a quick calculation, especially if we're dealing in we want to get this in your head that if you go to standard units, a lot of the equations will work out a lot nicer for you. Home, new slide, blank. Four-inch internal pipe at 400 gallons per minute. What is the flow rate in standard units? That was not, I don't know if that was intentional or not, but I was asking for the flow rate, so I was asking actually for Q. So the 4 inches had nothing to do with it. 400 gallons per minute. Goes to cubic feet per second the way we just did. Put the minutes on top, seconds down below. Put the gallons on below, cubic feet up top. And you multiply out. If in fact once you had the Q you wanted to get the area of course is pi over 36 square feet. So that would get you the velocity, which actually was not asked, at least is the one I've got here. So what is the flow in standard units? Flow is cubic feet per second. Velocity head is number 20, is in fact, velocity head is v squared over 2g. So that was probably one of the most straightforward problems on the test. 20 squared over 2 times 32.2 feet per second squared gets you feet of head. The next problem, 21. We just kind of talked a little bit about at home, new slide. 21, velocity water and a 6-inch, so you have to go from, right, from 300 gallons per minute to cubic feet per second, as you did before, and then you have to know that the area is going to be, compare and square, pi over 16 square feet, and you're going to take Q divided by area to get velocity. And then you're going to take that velocity, I think I gave credit if you, and then you're going to take that velocity and go velocity head, v squared over 2g. That's 21. 22. Purely, 22 is Q gamma H. You're given a flow rate in cubic feet per second, gamma in pounds per cubic foot, and the H. That gets you the power in foot-pounds per second, but of course you probably want to do it over 550, and that's going to get you the horsepower of the pump. 23. Pressure head. P over gamma equals 50 feet. Therefore, P equals 50 times the unit weight of water, 62.4. 24. Remember, velocity, if you double the velocity of the system, you increase the head loss because head loss is proportional to the velocity head. So it is 4 times. Number 24 is 4 times. Number 25, 33.9 feet of water. I'm going to go here, home. People did relatively well on that one based on memory, but what you have to realize is that basically air pressure, 14.7 psi is the same as 33.9 feet of head, because 33.9 times 62.4 gets you 2116.8 pounds per square foot. You convert that, you're at 14.7 psi, which is the same as 1 atmosphere, which is the same as 760 millimeters of mercury, which is the same, I think, as 29.62, that's probably a little iffy, inches of mercury, etc., etc. So you can only pull water up, and you can never actually get it up 33.9 feet. That is a theoretical limit at sea level. Water flows down energy, or down pressure I took. What is true of the pressure of the pipe when the hydraulic grade line is below the elevation of the pipeline? It is a negative pressure in the pipe. The energy grade line and the hydraulic grade line differ by a velocity head, v squared over 2g. Number 29 is not a tough calculation. Someone gives you Q minus Q times delta time equals delta S. You just must get your units in the correct units. So when one gives you CFS, minutes are not standard. You will need to put that into seconds of 360 seconds to get an answer of 360 seconds times 2 cubic feet per second to get cubic feet. Number 30. I'll do it here. Q equals Q equals velocity 1 times the area 1 equals the velocity of 2 times the area of 2. But the area's diameters are given, so what you do, you instead of just a direct proportion, it's a proportion to the square. So you take the proportion of d1 to d2 and you square it and multiply by the velocity. And then you have to decide whether it's faster or slower. So in this case, once again, it's going, you're given the velocity in the 8-inch pipe and you want to know the velocity in the 10-inch pipe, so it's going to be smaller. So it's going to be 8 over 10 squared, because the area, the diameter becomes up squared in the area, and then you're going to multiply that by the 3 feet per second. You will realize how quickly you realize most of the energy loss occurs then in the smaller pipes. Things do not lose much energy flowing through the city in those large pipes, depending how fast it's going. As they collect into a lot of water, they do, and they're moving quicker. But when things are not moving hardly with any velocity, there is very little energy loss, because energy loss is proportional to velocity head. Almost done. 31, 32, 33 was essentially this. I will do it again. Home. I will not do the calculations here. However, if you're given Q, you need to put it in CFS. If you're given a diameter, you need to get your area in square feet to get a velocity. If you have a system then that does something like this, you're going to calculate the velocity and put a graph here of one velocity head above that. You're going to draft the energy grade line directly from the free water surface to there. That's the energy grade line. And you then are going to offset, if you would, and do a bad job of it, the hydraulic grade line. And of course they vary by a velocity head. And the distance from here, the pipeline at any one point, is the pressure head. And if in fact this pipeline went above, if the pipeline is above the hydraulic grade line, this is a negative pressure. Of course, that's a negative pressure only if we talk about pressure in atmospheric, where in fact what's around us is 0. That is the exam. Learning to put things in standard units and apply with a formula sheet some basics of converting gallons per minute to cubic feet per second. That is a great program or calculation for you to put in your calculator. It might already be there for some of them. Thanks for listening. For those, I will post these exam scores today so you can see how you did on this one. We still need to get the books back from you and also your projects, except for the one that was so well turned in on time. And it looks great. Thanks for listening.